Hello everybody, my name is Dr. Amir Sandhu and I'm a senior lecturer in exercise physiology at Bangor University in the UK. Now today's special strength and conditioning episode is going to look at the training considerations for developing muscle strength. So let's get straight into it. The episodes, there's going to be a three-part series of which this is the first part, and it's going to be relevant to practitioners, to coaches, and also to athletes as well. So anybody that tries to use resistance training or strength training to improve their performance or it's their sport, then this is going to be a very important video to try and understand what actually happens in the body. So in the first part, we're going to look at the physiological and neuromuscular changes that happen as a response to resistance training. And that will form the basis for our understanding of how we can manipulate various training variables to get improvements in strength, in power, and rate of force development. We're also going to look at the selection of appropriate exercises to enhance our performance, and in the third part of this special video series we'll look at developing a training plan based on the principles of periodization. Okay, so those are the things that we're going to go through, and hopefully this will be the knowledge that you will take away from this video series. So before we proceed, we need to define some of the key words or terms that we're going to use throughout the presentation. The first is muscular strength. Okay, so this is the amount of force that the muscle has to exert to overcome a resistance. So if we look at the deadlift bar here, the athlete here is going to have to generate a force, or his muscles are going to have to generate a force to overcome the resistance of the bar. Okay, so that's muscular strength. Muscular power is the ability to generate that force or torque in the shortest possible time. Okay, so it's this rapid development of force, and it's commonly occurs in when you do explosive type activities. So sprinting is one of the best examples, but jumping for example in basketball is another such example. And I'm sure in your sport you could think of a time where you need to generate very large amounts of power in a very short space of time. So that's muscular power. The rate of force development is related, it has a very similar definition to muscular power, and basically it's looking at how quickly, over a second or a millisecond, that a muscle can develop its peak force. Okay, and this is something that is often described in training studies, so it might be a variable that they look at in an experimental study to see if different exercises or strength training approaches can influence the power or rate of force development. Now, when you look at the factors that affect muscle strength, you need to think about two major changes that are happening, two categories of changes, and within those categories there are lots of sub changes that are happening. The first are the physiological changes. So we know that when we do resistance training we're going to have myofibrillar hypertrophy. I've actually got a 4-part video series on myofibrillar hypertrophy already on this YouTube channel. The link is in the description. Please do watch that to understand more about physiologically how myofibrillar hypertrophy happens. But we also have changes in our musculotendinous unit. So the tendons also undergo a change. They also undergo an increase in cross-sectional area. So we'll talk a little bit more about what happens with that. And by far one of the most important and often neglected parts of the kind of changes that happen in the body from resistance training is the neuromuscular changes. So as athletes, as coaches, we need to give appreciation to the kind of changes that are happening to our neural circuitry to develop strength and power. So we're going to talk today about motor unit recruitment, rate coding, and neuromuscular inhibition. So let's start with the importance of progression. So any resistance training program will have people at various different levels. You'll have people that are elite athletes, and you'll have beginners. Whatever level you're at, you're going to have to involve gradual progression, this term called progressive overload. So you're not going to get strong within a couple of days or a couple of weeks. Often it takes weeks or months, sometimes years, to reach peak strength or peak performance. Okay, so gradual progression, it's acknowledging that the physiological changes, the neuromuscular changes, they don't happen very quickly. They take time, they take repetitive training and very structured and specific training. Now we do know that as we start to do resistance training, we're going to have an increase in the cross-sectional area of the muscle. So that's going to occur through myofibrillar hypertrophy. So literally the actin and myosin, which are the protein filaments involved in the muscle contraction. So the myosin head attaches to actin filaments, and it pulls the sarcomere smaller, makes it shorter, okay, and that causes a muscle contraction. So what you have to think about is those centimeter changes that you see at your bicep are occurring due to nanometer changes in the very minute or microscopic protein structures in your individual muscle fiber strands. Okay, so this is a cross-section of a biceps muscle. We've sliced it through. You can see these bundles of fibers, and inside those there's sub-bundles, and if we were to then divide those even further, we'd see these individual strings. They're made up of actin and myosin filaments. The actin is the thin filament here. The myosin are these thick heads that kind of attach to the actin, and they cause shortening of the sarcomere, and they're also kind of anchored by this protein called titin. So when you have myofibrillar hypertrophy, essentially you're having more of these actin and myosin fibers added in parallel, okay, and that means that you have more cross-bridge, more of these myosin and actin filaments attaching, cross-bridging with each other, making for a stronger contraction, okay. So that's what happens in terms of the architecture of the muscle. Now we know that if your cross-sectional area, so the size of your muscle is greater, so is higher, that relates, so from correlational analysis, that relates to greater force production. It makes sense physiologically. The more actin and myosin cross-bridge formation that you can have, the stronger muscle contraction you're going to have, the more force that's going to be produced. And this is actually some data way back in 1989 from a scientific study done by Häkkinen and Keskinen in the European Journal of Applied Physiology and Occupational Physiology. This can be found on Pubmed, Google Scholar, if you wanted to know a little bit more about what they did in that study. Now, one of the physiological thing that happens in the muscles is that when the muscles get larger, their angle of pennation also changes. So they almost go to this fan-shaped arrangement of the muscle fibers. Now, let's have a look at a picture. Now, in our body, we have various different striations of the muscle, various different types of fibers, and certainly the pennate muscles, the muscles that are involved in generating a lot of force, will have greater angle of pennation. So what we can see here is this is the tendon, this is the muscle, this is kind of like an imaginary line, longitudinal axis from the tendon, from the insertion point, and what we can see is that this kind of fan shape, this movement across like this, allows more actin and myosin cross-bridge, or actin and myosin fiber, to be able to be packed into this area, more cross-bridge formation and a stronger muscle contraction. And when you look at, say for example, this muscle here, which doesn't have this level of pennation at all, it's not going to be able to produce as much force because it's going to have a smaller cross-sectional area. So this kind of physiologic adaptation here, and we call it the physiologic cross-sectional area, enables greater force production. Now, when you have, like for example in Olympic weightlifting, where you have different weight categories, one of the ways in which the higher weight categories can produce more force is because they tend to get more angle of pennation in the muscles as they hypertrophy, okay? So you can have pennation angles of up to 30 degrees, and as I said before, they allow more actin myosin fibers to attach to each other, stronger contraction, more force that's produced, okay? So progression is very important because it allows some of those physiological and anatomical changes to happen within the muscle. Now, muscular tendinous stiffness is extremely important as well. It's very important, and we've got to give heed to it. So when your muscle contracts, it produces a force which acts on the skeletal system, on the bone, via the tendon. The tendon is transmitting the force produced by the muscle to the bone. So this point here is very important for force transmission, okay? Now, when you do resistance training, one of the things that will happen is that you not only will get bigger biceps, you'll also get larger tendons, larger, thicker tendons. So again, if we take a cross-sectional look at the tendon here, and we sliced the tendon, we had a look at what we're seeing again lots of fibers. Like with the muscle fiber, you're seeing lots of fibers. We can look at the different bundles, pull them out, pull out the individual strands, and would see microfibrils consisting of collagen. Okay, now when you do resistance training, as you lift more weight over time, your tendons will become stronger because there'll be more deposition of collagen. So more collagen will be produced, very complicated biochemical reactions will be taking place to enable the tendon to become stronger, to become larger, and to become stiffer. Okay. Now, it's very important that we have stiff tendons or stiffer tendons because they enable more forceful concentric and isometric muscle contractions. So this is a study done by Wilson back in 1994. Again, I've got the link in the description. So they looked at tendon stiffness and found that it does translate into increased performance. Okay. So in terms of how it does that, so what are the biological mechanisms for a thicker and stiffer tendon? Well, what it would do is if something is stiff, it won't deform as much. Okay, so if you have less deformation of a tendon, so if a tendon's thick, then less deformation, all of that energy or force will go straight from the muscle to the bone. There's no loss of the energy. Okay, it's very efficient, so it increases the efficiency in which force can be transferred from the muscle to the bone because the tendon doesn't deform as much. There's also more potential energy stored when the tendon is stretched, which then provides momentum when the tendon unloads. And what I've got here is an elastic band just to highlight this process. So we've got a thin elastic band and a thick elastic band. Now this thin elastic band, if a little bit of force goes through this, I don't need to stretch it, it deforms quite easily. Okay, and if I was to pull it, so I stretch the tendon, release it, yeah, there's a little bit of force, you know, there's a bit of a potential energy there which is released when I unload it. But when I look at the thicker tendon, or the thicker elastic band, which represents a thicker tendon, as I pull on the elastic band, I need to apply much more force. So much more force is needed to deform that tendon. But also, if I was to stretch the elastic band or the tendon just to here and release it, it gives a much more forceful kind of more energy. Okay, there's more potential energy in this thicker tendon, which is going to help in certain movements, so in sprinting, in jumping, sudden changes of direction, so all of those type of situations. If you're a boxer and you're throwing a fast punch, again, all of those situations will enable maximum efficiency from the muscle to the bone of the force transfer via the tendon. So that's just an example there to show you. Now, there is some scientific evidence to suggest that some structures within the sarcomere, so the sarcomere is the contractile element of the muscle that contains the actin and myosin and some other structures. So the actin, myosin and titin in particular may also increase in stiffness. So you have a stiffer sarcomere. Again, that increases rate of force development. Okay, so there is some research evidence to suggest there are some changes in terms of stiffness that are happening in the tendon and beyond the tendon as well. So those were some of the kind of physiological changes in the muscle and the tendon. We also need to look at what happens in the neuromuscular system. Now, we know, for those people that don't know, our muscles are innervated by nerve fibers, which are termed motor units. Okay, so the brain sends a signal from the motor cortex, from the cerebellum, to the muscle fibers. Some of the signals will also come from the spinal cord via interneurons, and they'll go. So you'll have what are called an alpha motor neuron. Okay, so this is an alpha motor neuron. You can see these tentacles here, which are called dendrites. These dendrites attach to other neurons, okay, like this, and they receive signals. They receive electrical signals. So, you know, all of the nerves in the body, imagine that they're communicating to each other via these dendrites, kind of connecting with each other, synapsing with each other. The electrical signal is received. It goes through what we call the axon here. The axon's got this kind of like fatty sheath surrounding it, which is, these fatty sheaths are consisting of Schwann cells, and they have these little gaps called node of Ranvier, and they basically allow the electrical impulse to speed up. So rather than go through the axon all the way to the muscle fiber, they'll jump from one gap to another really, really quickly. And so you have a very fast signal going from the spinal cord, from the brain to the muscle when you want a movement, and that's why we can make voluntary movements. You know, we think about something and we've probably done it before we've finished thinking about it. So cell body, axon, and then you have these motor end plates. This is where the nerve cells, or the neuron will attach to the muscle fibers, okay, to different muscle fibers, and you have millions of these motor units. This is just one example. Millions of these motor units activating different parts of the muscle to make a nice smooth contraction, and fibers in the different motor units. So, you know, this is one motor unit, you'll have another motor unit coming in, activating some fibers that this motor unit's activating here. So that allows a smooth contraction. You know, you don't have jerky movement, everything is working synchronously. Okay, so very important that we understand the basic anatomy of the motor unit and how electrical impulses are propagated to the muscle fibers. Now, what happens when we, in terms of training, in terms of strength training, is that we recruit different motor units at different times and in terms of the requirement for force, okay? So here again, I've got this for reference just so that it's into your mind. We've got the muscle fibers being activated by the motor unit. In 1965, a neurophysiologist called Elwood Henman found from his research that motor units are recruited according to their size, okay? So we know everybody's heard of type 1 and type 2 muscle fibers. So the type 1 fibers are more suited to endurance events. They're smaller in diameter as well. They have less force production. And they also have smaller motor units as well. By small, we mean that the cell body is smaller. If you've got a smaller cell body, then it means that these neurons can activate much more quickly. Okay, they can activate quicker when they receive a signal. So quite often, while I'm standing here talking to you, it's my small motor units that are being activated to move my hands and my arms. If I'm brushing my teeth, it will be the type 1 motor units, type 1 muscle fibers that are being activated. They've got a lower threshold for activation. So and then in terms of exercise, when you do moderate exercise and it's the type 1 fibers that are activated, conversely, those larger motor units are found in your type 2A and type 2B fibers. These are the fibers that are involved in doing muscle contractions that we can see here. Now these have a higher threshold for activation, which is good because it means that if I'm going to brush my teeth, I'm not going to be doing this, or if I'm standing here talking, I'm not going to be tense. You know, I'm not using those muscles that are producing greater force. Those type 2 motor units are going to have a larger cell body. Okay, this part's going to be much larger, and it's going to, obviously then the electrical signal will go to those type 2 fibers. Now, in terms of the difference, research has shown that the type 2 motor units, or the motor units that serve the type 2 fibers, the larger motor units, have a 50 times difference in force output relative to the smaller motor units. Okay, so there's such a big difference here. So what we really want to do in training is to start activating these type 2 fibers in our training so that we're able to also activate them and use them during during sporting performance. So I talked a little bit about force development thresholds. Motor units are extremely important because you have to reach force development thresholds to be able to recruit type 2 motor units. You don't recruit them otherwise in normal situations. Okay, now with training, there is evidence that you can lower this threshold, which means that you can recruit these motor units much more earlier, therefore that you're going to get greater force production because your type 2 muscle fibers are going to be coming into play much sooner. Okay. Now you may hear or you may read that there are other ways to activate type 2 fibers. So fatigue is one. So generally what happens with fatigue is if, for example, you're an endurance runner, you're running along and then you suddenly encounter a steep hill, you probably are going to get activation of your type 2 fibers. They're going to increase the force output. You'll be able to run up that hill. But that type of training is not optimized for weightlifting. Okay, that's still very endurance based, and those type 2 fibers are only coming in because the type 1 fibers are becoming fatigued as you encounter that hill. To develop type 2 fiber kind of increased force output and to get type 2 fibers activated early, you need to do specific resistance training. So that's extremely important. So in terms of the motor unit recruitment and altering it, research evidence has shown that ballistic training, which includes Olympic weightlifting as well, enables the best method of recruiting type 1 and type 2 motor fibers as well. So you're really using those type 2 fibers earlier in conjunction with type 1 fibers. So weightlifting is a very important methodology to do that. We're going to talk more about this in the second part. So in the second part, we're going to specifically talk about the exercises that you can use to increase some of these physiological neuromuscular changes. So essentially what research has shown is that when you do weightlifting or ballistic type movements, then you're going to have greater force production because the threshold for activating those type 2 fibers is lowered, so you have increased power. Okay, so the muscle will be able to produce that force over a much shorter time period, and that's applicable to a number of different sporting situations. So moving on then, another important change that happens in the neuromuscular system in response to resistance training is rate coding, and how that changes in terms of the activation of the motor unit. So before I continue, I need to define what rate coding is. So in this graph here, we've actually got rate of stimulation. So this is the amount of times the motor unit is activated, okay, with the electrical stimulus going to the muscle fiber. So if we look at here, this is the motor unit is activated 5 times. So 5 individual bursts of electrical activity go to the motor unit, and they will then activate that motor unit. That leads to very weak muscle contraction. It's not a strong contraction. In fact, one signal going through the motor unit to the muscle fibers is known as a twitch. Okay, that's just one motor unit being activated, but that can change all the way to tetanus. The tetanus is when all of the muscles or all of the motor units are activated, and there's lots of electrical stimulation going through those motor units. Okay, so lots of bursts of electrical activity, and they'll cause this contraction. And to the point where you just have this very nice, smooth blending of all of those individual bursts into one, then you get this nice, smooth contraction, okay? So the frequency of stimulation of the motor unit is extremely important in improving strength, okay? One of the things that resistance training does is it improves this physiological or neuromuscular or neurophysiological change. It coordinates that, so you have increased summation. So that basically allows lots of signals to happen. And remember, this is times per second. So we go from, with training, and as you increase the summation of the signal, you go from having 5 twitches per second, per 1 second, to having, say, 40 twitches or signals per second, so 40 electrical bursts through the motor unit to the muscle fiber, okay, and that will increase the contraction of the muscle and the strength of the contraction as well. So frequency summation is very important because it allows multiple contractions of the muscle fiber to occur, and it will happen very smoothly because those individual stimulations are summated together, so you get this smooth kind of contraction. Okay, now we don't really know what happens when you get to this kind of peak force. There is this concept called the staircase effect, or trepe, and essentially what happens is that when you're at complete rest and you start to build up the electrical input going to the muscle, so you're going to be lifting a very heavy bar, then what's going to happen is the force that's produced at these low frequency stimulations is going to be much less than when you get to the kind of higher end, to 40 to 50 rates of stimulation per second. And essentially what's happening each time you have this stimulation of the muscle, calcium is being released into the muscle cell. Calcium is extremely important. You cannot have a muscle contraction without calcium. So every time an electrical signal goes through the motor unit to the muscle fibers, calcium is released from the sarcoplasmic reticulum. It actually causes the myosin head to be able to attach to the actin filament to cause that shortening of the sarcomere and a contraction. So calcium is very important, but the thing is, as you get to these higher stimulations, calcium doesn't have a chance to remove itself from the sarcoplasm or the muscle cell, okay? So calcium builds up, and it's possible that enables you to have this very strong contraction as you reach towards tetanus, okay? So rate coding, this is how it actually works, and it's frequency summation. We're trying to increase the amount of bursts of electrical activity going from the motor unit to the muscle fibers to increase the contraction. So again, ballistic training has been shown to improve the amount of times a motor unit will fire, so the stimulation going to the muscle, and obviously the more stimulation that you get, the faster activation of the muscle. That's going to lead to increased speed, it's going to lead to increased strength, and obviously power as well. Now, for anybody that's interested, I've got the links in the description. Some really interesting research performed by Van Kutsem in 1998 and Leong in 1999. They looked at ballistic training methods and rate coding in young and old healthy athletic individuals. And it's a very good read to kind of see scientifically what's been shown from training and increasing the rate of stimulation to the muscle. So another adaptation that occurs when you do ballistic type training is that you don't just have one burst, or you don't just have a couple of bursts going through the motor units. You might have a double signal, what we call doublet signals, so 2 consecutive discharges within a 5 millisecond interval. So you have these, you almost have doubling of this frequency of the stimulation of the motor unit. So that's one adaptation that could occur. As I've said in the previous slide, you have increased firing frequency of motor units, but if that happens in different muscles, so if you're doing a very coordinated movement like this, and even training here as well, you're going to have increased force production from all of those muscles combined. And also this is a really nice study, if anybody's interested in reading further. Inoka back in 1995 showed that when the firing frequency of a motor neuron goes from minimum to maximum, the force that's applied by the muscle can increase by as much as 3 to 15 times, okay? So it's by changing the stimulation of the muscle, you're going to be increasing the amount of force that muscle can apply by quite a large amount. And the changing is going to happen through doing, ballistic type activities, Olympic weightlifting, any kind of muscle contraction that involves moving kind of heavy load at a very high speed. So you're accelerating quite powerfully. So another change, this is the final change that happens within the body, is the neuromuscular inhibition decreases. So neuromuscular inhibition is basically, if I was to go to the gym and see this deadlift bar and try to lift it, if I don't have the strength to lift that bar, then what's going to happen is as I lift it, the force that's going through from my muscles to the bone via the tendons is going to cause a decrease in neural drive. That's why we can't lift heavy things, because it's our body's way of protecting us. Because in our tendons, we have something called the Golgi tendon organ, which I've abbreviated here as GTO, Golgi tendon organ. So every tendon has these receptors, and essentially what's happening is when I lift something which is just way beyond my capability, then the Golgi tendon organ is going to send via the IB afferent sensory neuron a signal to inhibitory interneurons in the spinal cord. What those inhibitory interneurons are going to do is they're going to stop any excitable signals or excitatory signals going to the motor neuron. Okay, it's going to stop that from happening. So the muscle will then stop contracting, and well, it won't contract at all, and so therefore you won't be able to lift that weight. So it's very important that we take part in training which can kind of stop this inhibitory effect, and one of the ways that we can do this is complex training. Okay, now complex training, before I get onto it, is actually going to improve or strengthen not only the muscle but the tendons as well. So the tendons can handle a lot more force, so therefore it's going to be a higher threshold before the tendons send that inhibitory signal back to the spinal cord. Complex training is basically matching your traditional strength training with plyometric training, and essentially, so an example that I've given here is you'd do a traditional squat like you normally would, back squat, and you'd follow that straight up with a jump squat with weight. Okay, so there's lots of different complexes that you could do, that your coach could advise you to do, but there is evidence to suggest, scientific evidence to suggest, that complex training can reduce inhibition. Okay, can reduce this inhibitory signal. So again, this is choosing the right training will depend upon what it is that you want to achieve in terms of the outcomes of your sport, but it's very important to understand these kind of physiological changes that are happening. So that's the end of part 1. So what we're going to do in part 2 is actually look at the effectiveness of different resistance training programs to manipulate the physiological and neuromuscular adaptations that we've just talked about in this part. So we're going to focus on the advantages and limitations of all of these exercises, so body weight exercises. We'll have a discussion about machines and free weights. We'll look at Olympic weightlifting movements, ballistic training, plyometrics, eccentric training, and then we'll finish off with kettlebells as well. So please stick around for that part. I'll hopefully see you soon.